So on top of that, so thanks for this. So the title of my talk is SysML Tooling for Design and Engineering of System of Systems, and this is part of the Arrowhead Tools project. So first, some very few words on SysML. This is not a tutorial on SysML, but just to introduce it to those that may not have heard to it. So it's a general purpose modeling language for system engineering, and has been around for quite some while and is an extension of the UML language. So about 60% of UML is part of SysML, and that's the extension we see today. And we are currently in the phase of moving from SysML version 1.6 towards a version SysML 2 that is in the preparation by OMG, who is standardizing this and providing the specifications. And we have luckily a couple of people like Øystein Haugen and Geza Kulchar, and particularly Øystein Haugen is very, very active in this definition of the version 2.0. Tools that we're using, I have personally been using the Magic Draw Cameo, which is a commercial tool from the Magic Draw company, nowadays Dassault, and this is 1.6. And Papyrus is an Eclipse tool that is capable of doing 1.6, but it's also the primary tool where the development for the version 2.0 is happening. Today's discussion on system of system modeling will very much be based on service-oriented architecture. That means microsystems producing and consuming microservices. So this is the focus of today's thinking around system of system modeling. So what are the characteristics of these SOA microsystems? One very prominent one is lookup, requires a service registry, which is part of things like Arrowhead, the Arrowhead, Eclipse Arrowhead. We need late binding, then we need an orchestration capability, and loose coupling. Means that we only is connected when we are exchanging services. We can use push or pull based approaches for exchanging data. And a microsystem performs its function independently. It doesn't need any external information to actually make it the computation or actuation that it's designed to do. And a microsystem can be stateful or stateless. These are kind of the characteristics that we are considering here. Then it's clear that a microsystem produces or consumes one or several services, but we will probably not see a microsystem producing 100 services or consuming 100 services. Then it's maybe not a microsystem anymore. This is kind of a well-established area, and this is pretty well known. The new thing might be that SOA and microsystems here are put on the same level, and this is advocated by, for example, big companies like IBM. So this is also the approach I'm taking here. If we then look at the system of systems, there are a number of characteristics that has been set forth in primarily two papers by Meyer from 1998 and Bormann and Sauer from, I think that's from 2006 or 2008. And I have kind of merged these two into what you see on this slide. I will not go through this, but this is what it's about, and we need to have that in our back of our heads when we are trying to do this type of modeling. Geza, Øystein, and me has written a paper on how this is we'll work together with SysML, and that paper is currently in review at a journal. So hopefully, and that can be out rather soon. So the modeling of this system of systems we have done is based on Eclipse Arrowhead, and yeah, you know what it is, most of you. And we have made use of a number of these SysML modeling basics, from requirements diagrams all the way to sequence diagrams. And I will go through a number of these throughout this presentation. How do we support service-oriented architecture in SysML then? There is an old SOA ML profile for SysML that came out in 2009, hasn't been very well adopted in the community. So we have created a profile which is entirely based on Eclipse Arrowhead, and we have intended to support several of the engineering phases that has been defined both in the well-known standard ISO 81346 and in the extension that some of our very good friends here, Vito, John, and others have created throughout the work in the Arrowhead Tools project. So we will look further into this, and you will find that we are making use of this type of engineering approach. There is further developed a library of Eclipse Arrowhead core systems. And there is a template as well for a number of things where we can ease the engineering by having ready-made local clouds, system of local clouds, generic application system, models for devices, models for networks that are suited to the SOA thinking and to the way we think engineering of service-oriented architecture and solutions throughout the Arrowhead architecture and the engineering process, etc. If we look at all the systems that is being released and or in candidate status or prototypes or released other ways, there's a big number of them. The things that has been modeled is this. All the ones in solid line green rectangles here are modeled, and they are currently in the library. There is a couple of more things which are in the works, which means libraries and adapters to legacy systems like OpenCA, Modbus, Z-Wave devices, and we also look forward to Lightwave M2M devices, for example. But let's move to the engineering process. The top figure here is borrowed from Vito and his work on extending the ISO 81346. And the bottom part here is the ones that we have been including in the SysML profile. And that means requirements, functional design, procurement and engineering, deployment, maintenance and evolution. Operations is not included since we don't think SysML is suitable for that. And as you can see, we have divided the procurement and engineering into two parts. And I will explain that a little bit more in detail later on. So this is the engineering process. If we start to look at that together with the Eclipse Arrowhead, we can see that requirements, system of system requirements need to be addressed. We need use cases, all those kind of things. Then we make a black box functional design. That means that we are telling which local clouds we want to have, which core systems should be involved, which are the application systems and their services on a high level. The next step, we start to talk about which devices do we need to have. And we make the white box engineering of all these systems means that we start to look at all the internals of the application systems and how do we put code together, and can we then install core system and application systems on the procured hardware. And then we have a deployment where we actually put them into reality, and where we need to tell where are they, all these kind of things. So this is the high level view on the engineering process. If we then look at the architecture of a solution, we have taken the different levels of the thinking from Eclipse Arrowhead, and that means that if I think that in the middle here we have system requirements, or systems producing and or consuming services, now you see my pointer. This is one of the levels. These systems will then aggregate to a local cloud, and having multiple local clouds, they will aggregate to a system of local clouds. So the first level here is a local scale system of system, and the next level is large scale system of system. And we have selected to make this distinction because we're having this local cloud concept. Then, of course, all these systems, they are hosted, computed on something, which is devices. And these devices are connected to networks. So this is the kind of architecture dimension of this engineering thinking. And we have taken the step to combine the architecture and the engineering process in this way. And all the light yellow boxes you see now here this is basically what the SysML profile contains. And it provides us with a guidance on how we can work us through this. And I will guide you through all this using a use case. And we will come back to everything up to deployment. The maintenance and evolution part will not be discussed to any extent today. There is some initial thinking about a number of these things, but this have to, we've left that for a later occasion. So let's start with a use case. And I've chosen a use case which is well known in many areas. It's a tank control, well published, well understood, also well used at universities, and a reality in industry. And I've chosen it because it also holds real-time requirements, and it's a closed loop control. So nothing complicated about this, and we can also think that an installation holds multiple of these tanks. So we can think of having like 4, 5, 6, 10, 15, 20 of these tanks that does have its own control, which need to be protected and functional. So what do we first need to do? We need to create, in a SysML modeling situation, we need to make a use case. And SysML, then we make a use case diagram. And in this case, you will find the controller, the flow sensor, the valve, the tank level, the human user interface, and a control algorithm. So this is what it is. Doesn't look very complicated, but still it's quite an effort to build all these things together in a real world situation. We do need requirements on this. From a SysML perspective, we can do that in requirements diagrams. And I've just taken a few of those that I invented here for telling what's the various requirements that can be down there. And if we make these requirements more and more formal, we can also use them for checking that our solution actually meets these requirements. So if we have requirements, what do we want to do next? So yeah, these requirements, this is where we now are in this kind of architecture engineering matrix. So we are looking at requirements for the systems, the local clouds, and the system of local clouds. And someone may wonder, why do I not include device requirements and network requirements at this place? And so here I'm only thinking about functionality. I don't care who is actually doing it right now. So if we then look into the next step, what can I do? What should I do next from this? I should, of course, define which systems do I have. And in this case, I took the example of the flow sensor. And here we have the flow sensor and its service, which provides a flow. And I did, for whatever reason, I called the result here a flow level. So this is the flow level that's running through that pipe, which we are measuring. And you can also see that I indicate here that this type of system need to have a connection to a number of the core systems of the Eclipse Arrowhead to allow us to model the service-oriented architecture of thinking. Next, I'm interested in this, okay, who's going to talk to who? So this is the system of systems. This is the local cloud black box design. I have the controller, I have the valve, the tank level, the flow sensor, and the HMI. And these are the orchestration rules, basically, the exchange, service exchanges that we would like to set up. I haven't made anything to model the service-oriented things, since this is kind of standard and not connected to the functionality. The next step is that we can then describe the service exchanges and provide a swimlines, the interaction diagrams, telling how will they talk to each other. We have not included anything about authorization, all these kind of things that comes later and also comes quite automatically with the Eclipse Arrowhead architecture and implementation there. So that means that we now have come to the next level. So here we have made the black box design of the systems and the local clouds. I haven't shown anything about having multiple clouds, but it's clear that we can do that at the same time. We should do that at the same time. If we now had, let's say, 3 of these tanks that are at various places in our facility. So the next thing is to move to the white box engineering. And in an Eclipse Arrowhead language, this means that we are talking about the system design descriptions and the interface design descriptions, the service interface design descriptions. And in a SysML way, this will look like this. You will recognize the SysD here. This is the flow sensor design and the flow service, the service design here. Now we have extended this with the flow sensor design description, which now start to tell what is the protocol that this service is using. And I have, in this case, chosen to use co-op. And This is specified here. There is also things about telling which is the protocol, what are the type of certificates levels, encodings, and a couple of other things, metadata, that we will need to provide at this point of time. You can also see that we have the protocols used for talking to service registry, orchestration, and the authorization system. And I just indicated here that we used co-op for the service discovery. There is a prototype, or not released yet, but that will be in version 4.4, a released service registry with capability of talking co-op natively. And this, of course, need to be done for all the other systems that's part of our design. So this need to be done for all the ones that were in the functional black box design. And then we can create our local cloud. And here I have drawn all the interactions between our application systems and the mandatory core systems. And I also indicated that there are others if we need, for example, the gatekeeper and gateway later on. And the interesting part here is that we can also add now security policies. You will see that I have put these security images here, and there is also the security policies indicated. So that means that we're providing security policies here for the individual service exchanges. And of course, we can then model them in the way we like. I've just told here what's needed. We need a certificate, and we need a certificate of a certain, at least a certain type. And that's what we are telling. So security policies can be included in this case. And each of these lines also constitutes the orchestration, provides the orchestration rules. Who's going to talk to who? And these orchestration rules can, of course, then both the orchestration rules and the security things can then be used in the deployment situation, and should be used in a deployment situation later on. We'll come back to that. And from the SysML tools, I can extract the orchestration policies, the rules, and who's going to talk to who. So this is the ones, and of course, then the details of that. Where are they? Which are the URLs, and all those kind of things can be extracted from here. That would have been too small to show all that for you in a slide here. And I made a similar thing for table for the orchestration stuff, and here are the security policies that I, at that time when I made this excerpt, had put in there. So that shows now that with the white box design, we can provide both orchestration information and security information. If we then move forward and say, okay, here is the system of system level. And in this case, I made 4 of these local clouds. So these are 4 similar tank situations set up in that. And this is how they also are communicating via gateway gatekeeper and providing data to an MQTT broker. And it looks like that these two, LC1 and LC2, they have a usage of each other's information, and these two have a potential usage of each other's information. And that might be for a controller situation on a higher level. And all these things can be rather easily provided and modeled in SysML. And right now we have made the first white box, design description. And this is where we are. We are now within the procurement and engineering phase of the engineering process. Let's move on then. So let's look at implementation then, which is another part of the procurement and engineering part that we, in this case, have coined or named. And of course, here we now need to have devices and the hardware and network, that means that we need models for these as well. And in this case, I created both the black box of a device, a white box of the device, and an implementation of the device, and telling here which are the various systems that actually deployed on that specific hardware. And you can also see here that we have several types of networks in principle. So we have one network, so open internet. We have one which is just a local cloud network, and we have one network which is called the DMZ, the demilitarized zone. And there's a need for these things for certain reasons, since within our local cloud, we will only talk on this local cloud stuff. And these systems here will never exchange services to anyone outside that network. And the DMZ is just for gatekeeper, gateway, and onboarding, who have the need to talk to the open internet to find other local clouds or be involved in onboarding new devices, new software into our local cloud. We also created a router as a device here, and we have a device for other support core systems and a device for the application systems. And all these are provided in this library template, SysML, that's created. And then we need a model of the network. And here we have a model of the network internet side, the local cloud, the private local cloud, and the DMZ. And we can also here tell which are the various physical layers. So I've just, as examples, provided Wi-Fi, Zigbee, and Ethernet. And then we can choose which of these we actually make use of in our modeling of our real examples. So what have I done now from the engineering process and the architecture viewpoint? Now I have defined the requirements for the devices. I have defined the black box design and the white box design of those in the model. I didn't show you requirements table for the devices, but it's obvious that this is the place where we're going to do that. But now we are in the middle of this procurement engineering, so we've basically come somewhere here. Let's move on. So now we can start to see that I have a device with a number of the core systems. I have, which is only talking to the local internet, the private local cloud internet. I have one hardware, which is actually having two network interfaces, one talking to the private network and one talking to the DMZ, which is the only way to get out of our local cloud. This private local cloud just uses the router to get your IP addresses, these kind of things. And over here we have the 5 different devices for our flow meter, our level sensor, our controller, our HMI, and the valve. And this constitutes now one local cloud. We previously talked about having multiple of these tank setups, and for whatever reason now I just made 3 of them. So this is 3 different local clouds. So this is tank 2A, 2B, and tank 3C in a kind of imagined factory. And they are talking to the MQTT broker to actually enable information to flow outside of these local clouds to those who have the rights to access that. The interesting thing now is that if we just move back, when we have these here, which I should maybe move even further back. No, I didn't bring that in there. I didn't show that. So sorry. I thought I had another slide. I was busy. So when we come to this level here, this is the implementation, and in the models here of the implementation of, for example, the service registry, there is also information about where is the code, and at an implementation level here for each of these systems here, there is information about where is the code for these systems. And I can then extract that code. And this is a work that's not done yet, but from these extractions, we will be able to build Docker containers and provide the necessary code for a number of various hardware. This is something that our ITF friends are in the process of setting up now when we are fully with the Eclipse Arrowhead, and we will get some tooling from Eclipse, a CI/CD tooling for supporting that. So we will see a number of these hardwares to be set up, and there is a process that was started yesterday, which is led by Svetlin from ITIA, and with the support of as many as possible out there, telling which are the most important ones that we should provide to begin with, and ensure that we have tested at some certain hardware. So what have I shown now? Now I have shown that we can implement a system. That's the code. We have deployed that code on a specific device, and we have connected it with the hardware, and we've put it together into a local cloud, and we can bring all these things together in multiple local clouds. So the next step is deployment. How do we deploy these things in reality? Now we have hardware with all the necessary code on. We have routers, but where should they be? They need to be physically somewhere, and we can start to see these are the hardwares from a model perspective. To which network will they be connected, and all these things. And we can also then extract the network connections. So we can see from which point to which point we need to connect, for example, cabling. We haven't modeled power supply, these kind of things, but it's obvious that for each of these things, we also need to tell, okay, where is it? Where is it located? What's the network ID of the cable? What's the power connection ID, and all these kind of things. So this is a a way that we need to move. And when extracting all this type of information, we are looking into connecting this to various existing standards who have structures for how to name all these points. For example, where the network cable naming, the power cable naming, the naming of the devices, the naming of the software, and so on. And this is a kind of tedious thing to actually put all these things together, since there is not only one standard. I've just mentioned 3 of them here, but they are larger standards. There are too many standards out there, but this is a work that need to be done. And how do we make use of these standards, and how do we translate in between? Since some people are going to come with devices, oh, we are 10.303 based, others are BIM based, others are 15.926 based, and 12.008, etc., etc. So this is one of the interoperability issues that's still there to be solved, to really reduce engineering efforts in large scale engineering of very large scale smart environments, smart cities, smart factories, smart production environments, production value networks, etc. And you may remember that I spoke about these orchestration policies and authorization policies. This is also the time when we do deploy these and ensure that they are put at the right place in the right authorization system and the right local cloud. And this is maybe why I also then taken away that the system implementation is already done. Now we are working at kind of management of the individual local cloud and the management in between local clouds. And this is why we have made it this way. So this is the level where we now can deploy all these things in reality. So put them physically at the right place and making use of or providing this information in the models that will then be part of the documentation for the actual installation. So what about an engineering path then through this engineering process approach and the architecture, the abstract architecture model? So this is my summary of how we can think about doing such engineering. So first we start with the requirements for the functionalities. Next we create the functionalities and say, this is how things going to work together. And then we start to design the details, the interiors, and create the code and those kind of things. After that, we look at the hardware, the devices and the network, their requirements, their functional design, and their actual design description, which hardware, which operating system, which processor, etc., etc. And next, we then start to build all these things on an individual level together. So devices will be here with the necessary code installed, and so on. And next we come to the actual deployment. So this is the flow through this engineering matrix that we have put together. So what about these examples that I've made here? They are currently available on GitHub, and you see the link there. They will be moved to GitHub Eclipse Arrowhead under this repository name. We are in the process of checking IPR stuff, licenses, etc. and this is a thing that we are getting help from Eclipse to do. This is the link where this library is in the own cloud within the Arrowhead Tools construction. So they're there. You can play with them, the latest stuff is always at both places. They are connected. So once I updated it on cloud, I only push the things to GitHub at the same time. So what's next step? Where are we heading with all this? We are heading towards what I indicated, that there will be code packages available that we can deploy on a number of hardware types. This is something that started, and we are asking around. Svetlin already put up some, we'll create a matrix that will also be available, saying this is what it will be there, this is what's there now, and this is the plans for the future. And of course, these plans can be influenced by anyone by saying, hey, can we have it for whatever? Then we might come back and say, can you do that? Can you, here is a package, can you test it? And then we can see whether we can validate that. We say, okay, this is working at least reasonably good enough. Another next step is that there is a number of more things that's in the pipe, where we will make these models and make them available. And of course, together with these models, we will also make code available. So there is a few OPC UA adapters, and these will be modeled by and then code. So Apragita here in Luleå has one of these OPC UA things that we will model. Our friends at TWT made a Modbus TCP stuff, and that model is almost there. The code is there. There is a few things that I still haven't done to really make it useful. We have a documentation and code for Z-Wave. The models are not there yet. This is Salman Javed here at Luleå who has done that, and there is also a plan for making the same thing for lightweight M2M devices. There are model libraries in Python, the Calyx library, and C++, and these will also be modeled. There are still details on how should that be done, but let's find that out. And we're also happy to model other systems that people are using or developing, and making both the models and the code available to others. But what we need to do this modeling is we need at least a sysd description, an SD and an ID, given the Eclipse Arrowhead documentation structure, and for not yet in the GitHub repository, we don't have the templates for these yet, but they are in their own cloud. If you don't find them, ask me and I will give you the pointers. We also like to get pointers from you. Where is the code? Since we need to include that in the models to enable this type of extraction, putting global things together. And of course, you will get feedback on your documentation, possibilities to validate your results in a larger environment, and enable your results to be used by others. And just as I find every day when I'm on IEEE Explorer, this is what they say: increase your impact, increase your research impact, upload your code, and this is a way available. And in your paper, you can then point out that here's both models and code. So it's just a possibility that we will start to offer here. We are also starting to build simple examples of using all this Eclipse Arrowhead functionality that's here. And we're currently working with the prototype automation solution called Step Server here. And that will include things like an Eclipse Arrowhead Hello World example. How do we play the simplest thing with a service registry, orchestration system, authorization system? And how do you build your own application? How do you use other support core systems? How do you build multiple local clouds, security, etc.? And for the vaccine workshop that we're going to run in 3 weeks' time, many of these things will actually be part of the training packages that's planned for day 2 there. So this brings me to an end of my presentation, and I spent kind of 49 minutes or something like that. So I think I kept the time that I promised. So comments, questions, whatever. I'm happy to run a discussion with you on these things. Anyone?